Hello students, welcome to lecture 8 of chemical equilibrium. Next topic, calculating equilibrium concentrations. In the case of problems, we know the initial concentrations of substances, means initial concentration of reactants and initial concentration of the products, but we don't know the equilibrium concentrations. So to know it, there are some steps. The step 1, write the balanced equation. So first of all, we have to write the balanced equation. Let me take one example. PCl5 equilibrium PCl3 plus Cl2. Left side we have one phosphorus, right side we have one phosphorus, and left side 5 chlorines and right side 5 chlorines. So it is a balanced equation. Next, come to the step 2. Under that balanced equation, write number 1 A, initial concentrations of reactants and products, and B, change in concentration at equilibrium. Change in concentration at equilibrium. And C, assume one of substance concentration as X at equilibrium, then use the stoichiometry to determine other substances concentration in terms of X. Let me take an example. So the same example, PCl5 equilibrium PCl3 plus Cl2. It is a balanced equation. And in step 2, we have to take initial concentrations of substances. Initial concentrations. For example, I am taking here 3, and the reaction is not yet started. Then the product concentration 0 and 0. And at equilibrium, the concentrations. So reaction started and X moles of PCl3 formed and X moles of Cl2 formed. And the remaining reactant 3 minus X. So under the balanced equation, write initial concentrations and change in concentration at equilibrium, and assume one of substance concentration as X at equilibrium, then use the stoichiometry to determine other substances concentration in terms of X. Next, step 3, substitute the equilibrium concentrations in equilibrium equation. And solve X value. For quadratic equation, choose the mathematical solution. Quadratic equation, ax square plus bx plus c is equal to 0. And for this, x is equal to the formula minus b plus or minus under root of b square minus 4ac divided by 2a. Choose this formula for quadratic equation. And next, step 4, calculate the equilibrium concentration from the calculated X value. Calculate equilibrium concentrations from the calculated x value. And next, step 5, the last one, check the result. So these 5 steps are useful to calculating equilibrium concentrations. Let us solve one problem. 3.00 moles of PCl5 kept in 1 liter closed reaction vessel was allowed to attain equilibrium at 380 Kelvin and calculate composition of the mixer at equilibrium. And the equilibrium constant Kc is equal to 1.80. So here we have to find out that substances concentrations at equilibrium. Let us solve it. PCl5 equilibrium PCl3 plus Cl2. So this is the equation, and here the Kc is equal to 1.80. So that PCl5 dissociate into PCl3 and Cl2. So these are the products and it is a reactant. Now here the step 1, write the balanced equation. So this is the balanced equation, step 1 over. And next, step 2, write the initial concentrations under the balanced equation. So initial concentrations. So the PCl5 3.00 and the reaction not yet started. So here initial PCl3 concentration 0 and Cl2 concentration 0. And at equilibrium the concentrations x moles of PCl3 formed and x moles of Cl2 formed. And here the remaining PCl5 is 3 minus x. And what is the step 3? Substitute the equilibrium concentrations in equilibrium equation and solve x value. So we have to solve this x value. So here equilibrium constant Kc is equal to products concentrations divided by reactants concentration. So product PCl3 concentration and Cl2 concentration divided by PCl5 concentration. And Kc already given, the value is 1.8. 1.8 is equal to, so PCl3 concentration x and Cl2 concentration also x. So x into Cl2 also x divided by PCl5 concentration 3 minus x. 3 minus x. So 1.8. So this value comes to this side. To 3 minus x is equal to x into x, x square. 1.8 into 3, 5.4 minus into minus plus into minus minus 1.8 into x, 1.8x is equal to x square. And all these values comes to this side, then x square, then the minus become plus 1.8x, and here the plus become minus 5.4 is equal to 0. It is look like a quadratic equation. That quadratic equation, ax square plus bx plus c is equal to 0. So here the A value is 1, A is equal to 1, and B is 1.8, B is equal to 1.8, and the C is equal to minus 5.4. So the formula for quadratic equation, x is equal to minus b plus or minus the root of b square minus 4ac divided by 2a, and x is equal to, so what is the b value? 1.8. So here minus 1.8 plus or minus under root of b 1.8 whole square minus 4 into a value 1 and b c value, a value 1 and c value minus 5.4. 1 into c minus 5.4 and divided by 2 into a value 1. Then x is equal to minus 1.8 plus or minus under root of 1.8 square, the value 3.2, and minus into minus plus, and 4 into 1 into 5.4, the value is 21.6, and divided by 2. Then x is equal to minus 1.8 the plus or minus the root of 3.2 plus 21.6, 24.8 divided by 2, and x is equal to minus 1.8 and plus the root 24.8 value is 4.98 divided by 2. Then x is equal to minus 1.8 plus 4.98, 3.18 divided by 2 is equal to, if you do this calculation, we will get 1.59. Means the x value is equal to 1.59. So at equilibrium, the concentrations of substances PCl3 and Cl2 is equal to x. So here PCl3x and Cl2x is equal to x. The x value is 1.59 and PCl5 is equal to, at equilibrium, 3 minus x. So 3 minus x is equal to, 3 minus x value is 1.59 is equal to, we will get 1.41 m, and here also m, the concentration m. So we got that concentrations at equilibrium. At equilibrium, the PCl3 concentration x means PCl3 concentration is equal to, x means 1.59 m, and Cl2 concentration x. So Cl2 concentration is equal to, x means 1.59 m, and the concentration of PCl5 is equal to, at equilibrium, 3 minus x. So the value is 1.41 m, 1.41 m. So these are the concentrations at equilibrium. Next one, factors affecting equilibria. Equilibrium constant Kc is independent on initial concentrations. But if we change one or more reactants concentration of a system which is in equilibrium, then the system equilibrium will disturb and a net reaction takes place in some direction, either in forward direction or in backward direction, until the system restore new equilibrium. Similarly, if we change the temperature or if we change the pressure, the equilibrium will disturb. For example, I am taking a equation A plus B equilibrium C, and this reaction is at equilibrium, and the equilibrium constant Kc is independent on initial concentrations of substances. But if we change one or more reactants concentrations of a system, if I change the concentration of A, or if I change the concentration of B, or if I change the concentration of C, the equilibrium will be disturbed. Then to get new equilibrium state, the net reaction may goes to forward direction or backward direction. And similarly, if we change the temperature or if we change the pressure, the equilibrium will be disturbed. And here we use Le Chatelier's principle. Le Chatelier principle, and it states that change in any of the factors of a system will cause the system to change in such a manner so as to reduce or to counteract the effect of the change. Or the statement is, in other words, when a system experiences a disturbance in equilibrium, it will respond to restore a new equilibrium state. And in other words, if a chemical system at equilibrium and experiences a change in concentration or change in temperature or change in pressure, then the equilibrium will shift in order to minimize that changes or to counteract that changes. And this is applicable to all physical and chemical equilibria. So here 5 factors which affect chemical equilibria. Number 1, effect of concentration change, and number 2, effect of pressure change, and number 3, effect of addition of inert gas, and number 4, effect of temperature change, and the last one, fifth one, effect of a catalyst. Let us discuss the first one, effect of concentration change. The first one, effect of concentration change. When the concentration of any of the reactants or products in a reaction at equilibrium is changed, the composition of equilibrium mixture changes so as to minimize the effect of concentration changes. Let me take one reaction, H2 gas plus I2 gas and equilibrium HI gas. So this reaction at equilibrium, if we change the concentrations of reactants or products by adding or by removing, the composition of equilibrium mixture also be changes to minimize the effect of concentration changes. Means, for example, if I add more reactants or remove the reactants, the equilibrium will be disturbed. To get new equilibrium, the composition of a mixer also be changed. If I add more H2 to the reaction mixer, I adding more H2 to the reaction mixer. Already this reaction mixer is at equilibrium state. But if I add more H2 reactant to the reaction mixer, then the equilibrium will be disturbed. In order to restore the new equilibrium, the reaction proceeds in forward direction. That means added H2 react with I2 to form more Hi until attain a new equilibrium state. In the sense, H2 and I2 concentrations decreases and Hi concentration increases until attain new equilibrium state. Let me take one graph here. So this is the graph for this reaction. On y-axis we are taking the concentrations, on x-axis we are taking the time. So here this reaction already at equilibrium. So this is the equilibrium part. At time t1 I added more H2, then the H2 concentration increased. Then this reaction equilibrium state will be disturbed. So this part is not at equilibrium. And the added H2 react with I2 to form Hi. Means these two are involved in the reaction. Means H2 concentration and I2 concentrations will be decreases because these are involved in the reaction to form Hi. So H2 concentration decreases as well as I2 concentration also be decreases, but Hi concentration increases. See here, Hi concentration increases, and at time t2 the new equilibrium will be established. And here decrease the concentration of H2 and decrease the concentration of I2 and increase the concentration of Hi occur until attain a new equilibrium state. So first of all, this reaction at equilibrium state, I added more H2, then the equilibrium will be disturbed and the composition of equilibrium mixture changes until attain new equilibrium state. And the same point can be explained in terms of reaction coefficient QC. So here QC is equal to the product's concentration divided by reactant's concentration. Product Hi concentration power 2 divided by H2 concentration and I2 concentration. And at equilibrium, QC is equal to Kc. Already we know that. In this reaction, we are adding more H2. Then the QC being less than the Kc. So here, the QC being less than the Kc. Then the reaction moves in forward direction. Reactants to product. About the relationship between the QC and Kc, already we discussed in lecture 7. If QC is equal to Kc, there is no net reaction change. That will be at equilibrium and QC is less than the Kc, then the reaction move to forward direction, and QC is greater than the Kc, the reaction move to backward direction. So here we're adding more H2 than the QC being less than the Kc. Then the reaction moves in forward direction. And removal of product also boosts the forward direction, means encourage that forward direction. In the case of manufacturing of ammonia, the product ammonia is removed from the reaction mixer. Then the reaction keep going in forward direction to get more NH3. So here N2 plus 3H2 equilibrium 2NH3. So in the case of manufacturing of ammonia, that product of ammonia will be removed to get more NH3. And also in the production of CaO from CaCO3, the CO2 gas removed from the reaction mixer to get more CaO. So CaCO3 equilibrium and CaO plus CO2. In this reaction, removed CO2 to get more CaO. This CaO is used as a building material. So this is about effect of concentration change. Next one, effect of concentration and experiment. Here we are doing an experiment to prove that there is the effect of concentration on the equilibrium. Let me take one reaction. Fe plus 3 aqueous plus SCN minus aqueous equilibrium FeSCN, the charge is plus 2, and this reaction is at equilibrium. And this Fe plus 3 in aqueous, the color is yellow, and SCN minus aqueous, colorless, and this ion complex, deep red color, and this reaction is at equilibrium. And the equilibrium constant for this reaction Kc is equal to the concentration of products divided by concentration of reactants. Fe SCN aqueous plus 2 charge concentration divided by Fe plus 3 aqueous concentration and SCN minus aqueous concentration. Here I am taking one container. In that container I am taking 1 ml 0.2 m KSCN potassium thiocyanate solution. To that solution I add 2 drops of 0.002 m iron nitrate solution. Then the total solution gives the reddish color due to the formation of FeSCN plus 2 complex ion. The reaction takes place between the SCN minus and Fe plus 3. Then the reddish color FeSCN plus 2 complex ion will formed. due to that complex ion in the solution, that solution get reddish color or deep red color, and the intensity of red color become constant at equilibrium. So the reaction is at equilibrium. Then the equilibrium can be shifted in opposite direction, means product to reactant, by adding reagents, because that reagents remove the Fe plus 3 ions or SCN minus ions. Means here the reaction mixer is at equilibrium. If I add one reagent to that reaction mixer which is at equilibrium, by adding the reagent, what happening here, the equilibrium can be shifted in opposite direction, because the added reagent can react with Fe plus 3 or SCN minus. For example, if I add oxalic acid H2C2O4 oxalic acid reagent to that reaction mixer, and this oxalic acid react with Fe plus 3 ions to form a stable complex ion FeC2O4 taken 3 times, and the charge is -3, and it indicates decrease the concentration of free Fe plus 3 ions. And according to Le Chatelier's principle, the concentration stress of removed Fe plus 3 is relieved by dissociation of Fe SCN plus 2 to replenish the Fe plus 3 ions, and dissociation of Fe SCN plus 2 indicates decrease in the intensity of red color. Means here I am adding oxalic acid to the reaction mixer which is at equilibrium. Then what happening, that oxalic acid react with free Fe plus 3 to form a stable complex ion of FeC2O4 taken 3 times 3 minus. Means here decrease the concentration of Fe plus 3, because that Fe plus 3 react with the reagent of H2C2O4. Then what happening, this Fe SCN plus 2 will dissociate to replenish the Fe plus 3 ions, and that dissociation of Fe SCN plus 2 indicates decrease in the intensity of red color. So here if I add oxalic acid reagent to the reaction mixer, it decrease the concentration of Fe plus 3 ions. And if I add HgCl2 to this reaction mixer, it also decrease the intensity of red color. That HgCl2 will give the Hg plus 2 ions, and this Hg plus 2 ions react with the SCN minus ions to form stable complex of Hg SCN taken 4 times 2 minus ion complex. It indicates decrease the concentration of SCN minus ions, because this SCN minus ions are react with Hg plus 2. So there is a decrease in Sc minus ion concentration. So here what I am doing, instead of H2C2O4 reagent, I'm going to add HgCl2 reagent to this reaction mixer. Then that Hg plus 2 ions react with SCN minus ions to form a complex ion, stable complex ion Hg SCN taken 4 times minus 2, and it indicates decrease the concentration of free SCN minus ions and removed SCN minus is relieved by dissociation of FeSCN plus 2 ion complex to replenish the SCN minus ions, and dissociation of FeSCN plus 2 indicates decrease in the intensity of red color. So here this FeSCN plus 2 complex ion dissociate to replenish the SCN minus ions. That dissociation indicates that decrease in the intensity of red color. So in both the cases, complex ion going to be dissociate to replenish the Fe plus 3 ions and SCN minus ions. Then the reaction direction is reverse direction, means product to reactant. And this is about effect of concentration and experiment.